So today I want to talk about three fundamental concepts that I think every student should be aware of and have a well understanding when going into organic chemistry. If you have a strong foundation in these, it will make your learning process in organic chemistry so much easier. So the first one I want to talk about is hybridization. So hybridization. So hybridization. So what is hybridization? Hybridization is the combining of atomic orbitals to form these new hybridized orbitals that are lower in energy. Okay, and so you can have three types around carbon. You can have sp3, you can have sp2, and then you can have sp. All right, and so these are the three types of hybridization that you need to be aware of, and they each have unique properties. So let's just look at an example of each one. So an example of sp3 would be something like methane. So it looks like this, right? An example of an sp2 would be something like ethene. So here we have ethene. And then an example of sp would be something like acetylene. All right, so there's acetylene. Now, notice that each one of these hybridized carbons have a different geometry, all right? And so that geometry allows for different types of reactions to occur. But not only do they have different types of geometry, they also have different types of bonds. So if we look at methane, it is made up of sigma bonds, okay? If we look at ethene, we have a sigma bond plus a pi bond, all right? So that's what gives us a double bond. And then for acetylene, we have a sigma bond plus two pi bonds. And it's important to note that pi bonds are weaker bonds than sigma bonds. So sigma bonds are due to the overlap of hybridized orbitals head-to-head, where pi bonds are the overlap of orbitals from side to side. So you don't get as much overlap as you do with a sigma bond, therefore it's weaker. Now, I mentioned that these have different geometries, okay? And so for methane, an sp3 hybridized carbon, we have tetrahedral. For ethene, we have, this is called trigonal planar. And then for acetylene, we have linear. All right, and each one of these have a different bond angle. So if we looked at methane, the bond angle between hydrogen and carbon is 109.5 degrees. So 109.5 degrees. And if we looked at the bond angle between carbon and hydrogen on ethene, we would see that it's a bond angle of 120 degrees. And then if we looked at acetylene, we can see that it is, since it's linear, the bond angle is 180 degrees. So when you think of hybridization and you see a carbon and you're asked, what's the hybridization of the carbon? All you got to do is look and see if it's a single bond, double bond, or triple bond. And when you determine what hybridization it is, you need to automatically know that it's geometry, whether it's tetrahedral or not, and you need to know its bond angle, if it's 109.5 or if it's 120 or 180. And if you know those, then that will make your life in chemistry and learning chemistry so much easier. All right, so let's just move on from there. So another very important concept that I think you need to understand is pKa's. So I know when I took organic chemistry, we were taught pKa's, but I never really seen the importance of them. And then when I went off to grad school, I finally found out, wow, how important they are. And because the reason why is we know that pKa is the acid ionization constant. So pKa, acid ionization constant. All right, so what this tells us is how readily a proton dissociates from something that it's bonded to, right? So it tells us the acidity. And the reason why this is important is because down on, if we think about organic synthesis in general, it's all Lewis acid and base chemistry. And so being aware of different pKa values can really help you figure out what's going to react with what when you have a bunch of things just in a mixture. And so you need to be familiar with your general functional groups. You need to have a rough idea of where their pKa's are, right? So for an alkane, pKa would be approximately about 50. For an alkene, it's approximately 45. All right. If you have, say, a amine group, so say some RNH2, right? That pKa is approximately 38, right? An alkyne, so an alkyne is somewhere around 25, all right? An ester, so an ester pK is around 25 as well. Ketone is approximately around 20. And then you have alcohols, so your ROHs can range somewhere between 16 to 19, depending on the type of alcohol you have. Water, this is a very important one. If you learn any pKa, you need to learn the pKa of water. And the pKa of water is 15.7. All right. And then there's a few others that you could learn. Another very good one to know is carboxylic acids, right? So something like ROH has a pK of 4.75. And then lastly, I would say hydronium. So, all right. And hydronium has a pKa of approximately negative 1.7. So if you learn these, it will make your studies in organic chemistry so much easier, because this is going to be one of the things that governs reaction synthesis. All right. So lastly, I want to talk about arrow pushing. All right. So arrow pushing. All right. Arrow pushing is very important, and I see a lot of students get confused on pushing arrows. But being able to understand what an arrow represents is so critical to organic chemistry. Because if you don't accurately represent where electrons are moving, you can get confused, and it's easy to get lost when you're drawing mechanisms and really distinguish what's happening in a mechanism. And so there are two types. There are double-headed arrows. This is really bad. Let's do another one. So a double-headed arrow. All right. So we draw a double-headed arrow when we're moving 2 electrons. All right. Or you can think of it as a lone pair. So lone pair, or a pi bond. So something like that, if you're moving one of those bonds. All right. And then next is a single-headed arrow. And so we draw something like this. All right. And this represents the movement of one electron. All right. And so you typically see this when you're moving radicals. All right. And so, for an example, you could have a bond that may break. So, for an example, like Br2. And if you were to undergo a radical reaction, you would have initiation. So one arrow would go there, one arrow would go there, and that would end up giving you Br radical plus Br radical. All right. So there's a couple of examples. All right. So these are very important. All right. And you need to be familiar with this because when you start drawing resonance structures, you need to know which arrow to use. All right. Now, I also want to stress the importance of how you draw your arrows, not necessarily whether it's double-headed or single-headed, but where it points to, all right? So, for an example, if I just drew something like, let's see here, let's draw O minus, and let's just say plus some electrophile. All right. Now, put my lone pairs here. Now, if I wanted to show this reaction mechanism giving me this product here, there's only one way I can draw the arrows, all right? I can't draw the arrows from the electrophile to here. That would be incorrect, all right? Because the electrophile is electron poor. It's wanting electrons. And so that's not where the electrons are moving from. You have to have electrons for you to be able to form a bond, and the electrophile doesn't. So that would be incorrect. All right. So the next possibility would be, okay, if this is the electrophile, then this over here must be the nucleophile. So this would be the nucleophile. So that means the nucleophile must be giving its electrons to the electrophile. All right. It loves to give its electrons. It's electron rich. And the electrophile wants electrons, so it's going to want to take some from the nucleophile. And so the electrons are going to have to flow from the nucleophile to the electrophile. All right? Now, the proper way to do this would be to go, these electrons, whoop, had it on. Forgot I had it on erase. There we go. The proper way to do this would be, all right, we take our lone pair here. Arrows go here. And then these arrows go here. All right. That would generate our product shown here. Okay. How you do not want to do this is if you had it like this. You want to be very careful. Professors get very picky when it comes to drawing arrows, especially your organic professors. You don't want to do something like this. Okay? That means nothing. That is drawing arrows to space. All right? As organic chemists, they're very particular on how they want you to draw your arrows because, again, it means something. If you were drawing the arrow to here and just stopped here in space, well, then that's just saying that that charge is just floating around somewhere and it's not attacking the electrophile. And we know that's not what's happening. What's happening is we're generating this product here. So you want to be very careful at how you draw your arrows. Another thing is you don't want to draw your arrows to something that's more electron rich, right? So if we had something like, let's say we had this, all right, and we had, let's think of something here. I guess for the example, let's just do this, right? This is not a typical reaction you would see. But you're not going to have an oxygen, all right, attack a bromine. That's just not going to happen, all right? You've got something that has plenty of electrons attacking something that has plenty of electrons. And so that's not what's going to happen. You're going to want to have something, that really wants to give its electrons away more. You don't typically see a heteroatom attacking another heteroatom. So that's things to be aware of. Another little side note is if you have, say, something like this, right? You wouldn't want to say, oh, your nucleophile can come in and attack here and make this leave, all right? Because that's not what happens. You're always going to break the weakest bond first, right? And so your weakest bond in this scenario is the pi bond, right? And so what would actually be happening would be something a little bit different. You would actually have your nucleophile come in and attack your pi bond, and it may attack here or it may attack here, but the idea is you're going to break this bond here first, right? So this bond here, circle it in blue, is going to get broken first. All right, so these are just some important things that you need to take into consideration when studying your organic chemistry. And I promise you, if you keep these three things and in your memory tucked away, the concepts of them, it will make organic chemistry so much easier. All right, like and subscribe to the channel and hang around for more videos.